Okay, so this is Michaela Burns and Janaea Burns' project, and we're going to start off with our first question. And a 2.54 gram of beryllium chloride is completely dissolved into 50 milliliters of water inside a beaker. Our first question asks us to draw a particular representation of all species in the beaker after the solute has dissolved. Your diagram should include at least one beryllium ion, one chloride ion, and 4 water molecules. Make sure the atoms and ions are correctly sized and oriented relative to each other. So in order for us to do this correctly, we have to have the beryllium ions, the chloride ions, and the water molecules. So this is the H2O molecule. As you see, the oxygen and the 2 hydrogens. This is the beryllium ion, and that's the chloride ion. The beryllium ion is going to be attracted to the oxygens because the oxygens are negative and the beryllium is positive. And the chloride ions are going to be attracted to the hydrogen ions because the hydrogen ions are positive and the chlorine ion is negative. So that's why you have to make sure they're oriented to the right way, so that way the right things are attracted to each other. Okay, next asks, what is the concentration of beryllium and chloride ions in the beaker? So here we're giving the concentration is molarities, so moles over liters, and we don't know our moles or our liters. We have 2.5 grams of beryllium chloride, and we have 50 milliliters of water. So you start off with we want to find our moles, so you start off with the 2.54 grams that you're giving, and then you divide it by the molar mass, which is equal to 1 mole, so simple stoichiometry, and then you get the 0.03178 moles of beryllium chloride. And you take the 50 milliliters and you divide it by 100 to get 0.05 liters, and then you take your moles over your liters, as you see there, for molarity, and you get an answer of 0.635 molarity. Next question says, a solution of 8.5 molar lead nitrate is then titrated into the beaker, causing a precipitate of lead 2 chloride to form. Identify the net ionic reaction occurring in the beaker. So now that you have more into the beaker, we have to have a new equation. So you're going to have your lead nitrate plus your beryllium chloride. It's going to make a precipitate of lead chloride and beryllium nitrate. And then so that's your precipitate. So when you make the net ionic equation, you're only going to be using the ions necessary for it. So then you have the lead plus the 2 chloride ions, and then it's going to make the lead chloride. Next question asks, what volume lead nitrate must be added into the beaker to cause maximum precipitate formation? And here we're going to go back to our equation that we set up. Okay, so you're going to start off with the 2.54 grams of beryllium chloride and do molar mass and find the moles. And the number of moles of beryllium chloride is equal to the number of moles in lead chloride, which is our precipitate. And everything has a 1-to-1 ratio, and so you know how many moles there are. And the number of moles of lead chloride is equal to the number of moles of lead nitrate. So you have 0.85 molarity is equal to 0.03178 moles over liters. And then so liters is equal to moles over molarity. And liters is equal to 0.037 liters or 37 milliliters of lead nitrate. And the reason why that was so simple is because everything has a 1-to-1 ratio. Nothing has any 2s or 3s or 4s or anything. if it did, then the problem would be different and it wouldn't have been so simple, or our ratio would have been different. Okay, next question asks, what is the theoretical yield of the lead chloride? So then we take the number of moles times the molar mass, and then it goes to grams, so you have the 0.3178 times the 278.1094 grams of molar mass of PbCO2, and you get 8.838 grams of lead chloride. Students performing this experiment suggested the following techniques to separate the precipitate from the water. The teacher rejected each idea, explained why the teacher might have done so, and named the inherent errors of boiling off the water and decanting or pouring the water off. Okay, so the first one to discuss is why it's not good to just simply boil off the water. This is bad because you can also boil off some of the precipitate, and then at the bottom you'll be also mixed in with the spectator ions, and then so you'll have a really large massive precipitate, which would be inaccurate because it would also be mixed with the spectator ions. Okay, the next question is, what's wrong with decanting or just simply pouring the water off? One of the main problems with just simply pouring the water off or decanting it is you can also pour out some of your precipitate, and there's no way to get the spectator ions without that. So the best way to actually get just your precipitate is to drain off the water using a screen, a film, so that way you get only your precipitate, and then you let them dry out, so that way you can separate. So that way you can have just your precipitate, and then you won't have the spectator ions, because the spectator ions in this case are aqueous, and then also you won't have any of the spectator ions left behind from boiling. Okay, so part 2 of our AP question is completely different. It starts off with a chart that gives us different substances, gives us a boiling point, it gives us a bond length, and it gives us the bond strength of 4 different substances. It gives us the bond, it gives it of hydrogen gas, nitrogen gas, oxygen gas, and chlorine gas. The numbers are kind of hard to see, but to certain questions we re-say the information that they have given us. Okay, the first one asks for us to explain the difference in the properties given for the bond strengths of nitrogen gas and oxygen gas. Nitrogen gas is going to have a 226.8 kilograms per mole, kilometers, I don't know how to say that, well, I don't know that unit, versus the oxygen that has 118.9. The nitrogen gas has more bonds, so it's going to have a higher bond strength because they're going to be a little bit closer. And the oxygen only has 2 bonds, so the bond strength is going to be a lot weaker, which is going to make it easier to break. So the closer the ions are, the harder they are to break because they're going to be stronger. Okay, next, they asked about the bond lengths between hydrogen gas and chlorine gas. Hydrogen gas has a 0.75 and chlorine gas has 1.99. Hydrogen gas has a single bond, and it has a bond order 1, and it has a shorter length because it's a single bond, so there's going to be a higher pull between the two atoms. So because it's just one bond, it's going to have more pull because it wants to be stronger than what it is. And the chlorine is going to have also one, but its lengths are bigger when it's added together also because of the size of the atoms, and that also has a lot to do with the reason why hydrogen is shorter than the chlorine. And then there's chlorine has a bigger ion than a hydrogen ion, and there's a typical periodic trend which is increases across a period, but it has to do with the bonds and the size of the actual ions as to why one of them is longer than the other. Okay, and the next one asks the difference of the boiling points of O2 and CO2. This one also has to do with the size of the molecules. As you see, chlorine boils a lot higher than what oxygen boils at. And it has to do with the size of the molecules. Chlorine has a bigger molecule than O2. And then it has to do with the amount of kinetic energy it takes to boil off either one, and then also the amount of bond strength. So chlorine's going to be a little bit harder to get those ions and those particles moving a lot faster than what it would for O2 because they're just simply moving faster. So it takes a lot more energy. And it also has to do with the London dispersion. So that also has a lot to do with it. And then lastly, to ask, why are H2 and O2 gases at room temperature, while H2O is a liquid at room temperature? And the hydrogen bonds are the reason. The attraction of the gases themselves are much weaker, but the forces of the chemical bonds are way stronger. Also, the distance between the H2 bonds are shorter, which is why the strength is very strong. The H2 and O2 gases have a longer bond length, which make it weaker and easier to separate. And it also deals with being nonpolar and polar. The hydrogen bonds the water molecules are polar, and so that also has a lot to do with it. Okay, that was our video. If you guys have any questions, me and Michaela are here in the room and you guys can ask us. If you guys still need help on understanding anything, feel free to ask. We feel as though we have grasped the topic very well and that we understand the differences in the different periodic trends.